Hey guys, I'm Pat Kelly. Okay, this is a great problem to understand what's going on, and if it looks like the mathematics that you're actually going to do is going to be involved, it's not too bad. Okay, I've already got the formulas up here if that's what's intimidating you, but I'll show you how to use them and show you how to get our answers. But in terms of what's going on, you've been using the trapezoidal rule and the Simpson's rule to approximate the value of some of these definite integrals. And in order to do so for either of those approaches, you are slicing up the areas of the overall integral and then finding the value of each small area, okay? And also, remember, you're only finding an approximation. And I remind you of all that because the whole point of this type of problem is we have to find out how many slices to take. What value of n will make that approximation that we're getting within a certain error margin. Okay, so they give us this definite integral from 1 to 3 of 1 over x dx, and they specify that they want the error to be less than tenths, hundredths, thousandths, 10,000ths, 1/100,000th, okay? Or in our neighborhood, I guess we would say 0.4 zeros and a 1. 1/100,000th. There's a reason I'm saying that too, so I'll get back to that. But in this problem then, for either of our two approaches to approximating that integral, we have to find the value of n such that the error is less than that given threshold. Okay, so what it really comes down to in either case is knowing how to apply this error formula. Okay, and so what I'm going to do is apply the particulars to our integral to this formula, and then talk a little bit more about how to find that value of n in order to satisfy our threshold. Okay, so in order to get going, notice I do have a second derivative involved, f double prime of x. And while I'm at it, I also have a fourth derivative. This will be the second part of my problem, but I'm looking ahead. I need a fourth derivative. So what I'd like to start with, maybe just with some scratch work, is let's find those derivatives and be ready when we need them. So from the original integral, our f of x, remember with these formulas, the function, the f of x, is what's inside. So 1 over x, let's call it x to the negative 1. And then we can start taking some pretty quick derivatives, I think. I think they should be pretty quick. Minus 1 in front, drop a power. F double prime of x. Minus 2 in front, there's already a minus, so positive 2, x to the minus 3. I do need that fourth derivative, so let's go 2 more steps. Minus 6, x to the minus 4th, and that fourth derivative positive 24, x to the minus 5th. Okay, that was the most intense calculus that we'll do in this problem, but we do have a little bit of an algebra challenge. Let's get to that. Now, in order to apply the particulars for this problem into this formula, I know from the formula that the error that we'll have if I use the trapezoidal rule will be less than or equal to b minus a, that's your 3 and your 1. 3 minus 1 is 2. I got to cube it here, so I'm going to have an 8 in the numerator, divided by 12 times n squared. What was my n? Oh, that's right. We're solving for n. So you're supposed to have an unknown n here. And you'll see that the algebra that we do will be finding a value for that n. Okay? So let's keep going in the formula. And at first, this sometimes throws people. They think, hey, there's another variable. There's an x. But what that part of the formula is actually saying is, what's the highest value, the maximum, of the second derivative for any x's that are between a and b? So between our 1 and our 3, we need to come to our second derivative, okay? And that's, let me even do a quick rewrite. That's 2 over x cubed, which I'm only doing as a rewrite because think about this function. You know this function, at least without the 2. I'll do a quick sketch just down here, just a real quick sketch. You know that it basically looks like this, right? And my point is that on the x-axis, the highest that value is going to get is when x equals 1. It's the highest we're going to get with the second derivative. So this entire square bracketed expression is going to be when the second derivative is evaluated at 1. It's going to be the highest point. So I'm going to put a 1 in right there. 2 over 1. This is the cool part, is that maybe unknown part of your formula simplifies to a 2. Okay. And I'll do one more step here on this line in terms of just multiplying by the 2, or I guess the 2 and the 12. I could cross out and get a 6. 8 over 6, so let's say 4 over 3 n squared. Okay. All right, now back to what they asked us to do, though, is to keep, this is an expression for our error. We know that our error is going to be less than that 4 over 3n squared, but they asked us to make sure that that error is less than this 1/100,000th. So what we want is for that 4 over 3n squared to be less than, this is why I was saying it out loud a couple times before, 1 over 100,000 as a fraction, because I like the fraction form here better for my algebra that I'm about to do. So let's go ahead and play with the algebra of this inequality. It's not too bad. I'll even do a cross multiply to start, so I'll get 400,000 is less than 3n squared. And I'm sure you're a good enough algebra student to say, well, wait a minute, be careful. When you're dealing with inequalities, you have to watch out. Sometimes the sign of the inequality changes. Yeah, you're right. But only when we multiply or divide by negative, and I didn't there. Okay, everything's positive, including the n. Not just because it's squared, but remember what n stands for is the number of slices you're going to take. So n will be positive. That's important to realize for the next little algebra step that I'm going to do. Because what I'd like to do to solve this inequality is divide over the 3. That's easy. But also take the square root to get n alone. Now, very much so ordinarily, you have to be careful with quadratic inequalities. You take your time, you slow down and do critical values maybe, or a different approach. You learn factors sometimes in order to do that. But the algebra is straightforward, or I guess I should say like not dangerous, because everything's going to be positive. So in my next step, I'm going to divide over that 3, and I am going to take the square roots, because nothing bad's going to happen with all these positive numbers. And if you don't mind, I'm also going to switch. I like my n to be on the left, which means this less than does become a greater than sign because I'm switching things. And then square root 400,000 divided by 3. All right, great. Great, because we've gotten down to an n expression. I don't want to say n equals. We're saying n greater than. Square root of 400,000 divided by 3. I'm going to grab my calculator for that one, okay? So grab something in order to do that, make it easier. Square root 400,000 divided by 3. Enter. And I am getting that n has to be greater than 365 point, and even if I just go to 2 decimal places, you could go to 1 decimal place, because you always go up from here. Even if it doesn't look like it should round up, what I'm going to say as a final answer is that n equals 366. So I don't care how many decimal places you go to, because you're always going to go up. And the reason for that is that if I get up to 366, which I know is a little bit bigger than the number that I just had in line before, I know that I'm going to be satisfying this inequality. Satisfying this inequality tells me that if I get 366 slices in this trapezoidal rule, the error when I'm calculating this definite integral using the trapezoidal rule will be less than that 0.00001. Good work, good work. I'm going to go on to my part B, but I hope you're realizing what we just did. Some of the trapezoidal problems that you've been working on gave you an N, remember, and you had to do that work? Imagine doing it for 366 slices. All right, good thing they didn't ask us to do that. Let me move over to Simpson's rule. Exact same thought process here, so speed it up a little bit. I am now looking for the error margin using this formula. And I'll apply my particulars. B minus A is still 2, this time raised to the 5th power, so that's 32 divided by 180 times an unknown n to the 4th power. That's what I got to figure out. The maximum value of the 4th derivative of the function when x is trapped between that 1 and 3. So this is why if I go back over here, I did do the work ahead of time for the 4th derivative, 24 over x to the 5th. I won't bore you with a graph because it actually looks pretty much the same, right? 1 over x cubed and 1 over x to the 5th. Same looking graph. The point for us is that that maximum value is going to occur when x equals 1. So put a 1 into your 4th derivative and you get 24. Okay? Let me slide over just a little bit of space to simplify this, kind of like I did in the previous problem too. So I'm going to try to do this quickly. The 24 is 12 times 2, and I'm doing that because I know that the 12 does go into 180 15 times. So if I simplify that 12 with the 180, I'm going to get a 15 downstairs, n to the 4th. A 2 would have survived here, and I'm going to get 64. Check that. Just grab a calculator even, right? Okay. So what I did is I simplified the expression for the error using Simpson's rule. And now I'm going to add on the layer of, hey, I want the error to be less than that 1/100,000th. So this gets down to what we want again. What we want is that expression, 64 over the 15 n to the 4th. And we want it to be less than 1/100,000th. And just like before, we end up with an inequality that we need to solve. So I'll cross multiply. I again don't have any worries about anything goofy happening with the inequality. Everything's positive. So this would look like this. That's a 6,400,000. I'd like to divide by 15 and also take the 4th root. So I'm going to end up with n greater than 4th root of that 6,400,000, but divided by 15. And heck, I'm not going to tax my brain right now, even trying to simplify with a 5 in the 15 and a 5 in the other number. I got to go to a calculator, especially because of that 4th root. So let's grab a calculator and do a 4th root of 6,400,000 divided by 15. And I am getting n greater than 25.56 if I round. But even like the commentary added before, the rounding doesn't matter because your answer, you've always got to bump up in order to make sure you meet that threshold. We're going to say n equals 26. All right. Good. Now let me wrap up by suggesting that the work you did, great. A little bit of algebra, a little bit of understanding how to use the formula, tiny bit of calculus. But now compare the answers. If you're going to use the trapezoidal rule and you want your error to be less than this threshold, you've got to take 366 slices. Whereas the Simpson's rule can give you that same precision, but in only 26 slices. So it's a lot more efficient for this particular integral anyway. Okay, Hope that helped. Hope it helps you with some of the other homework problems that you're going to do on your own too.